Hi, welcome back, kiddos. Let's move forward. In your notes, here is a summary chart, but I think these are best figured out than memorized. So I'm going to leave this for your reference. But here's the deal. This is what we're after. The answer to your question is always going to be what has to happen in order to relieve the stress and get back to equilibrium. So let's take a look at this example. Again, the good old Haber process. We've got nitrogen gas plus 3 hydrogen gas yields 2 ammonia gas. Now, I'm going to show you a trick. That's a G there, sorry. Now, notice that it says negative 96. That means that it's exothermic and the heat is a product. That will help us as we look at the effects of temperature. Now, let me show you a couple of things. First off, a phrase. If you add, you have to subtract. And if you remove, you must replace. Some of you might like a little phrase better than the trick I'm about to show you. So let's take a look at this. The stress here is to add hydrogen. Now I'm going to put a line in here that's going to represent equilibrium. So that line represents a system that's at equilibrium. Now let's take a look at what the stress was. The stress was to add hydrogen. So I'm going to lift up the hydrogen side. Now, remember that the answer to the question is what did we need to do to relieve the stress or get back? So our answer to the question will be to consume reactant and form product. So if we lower the line, we're going to shift to the product side. Remember, if you add, you have to subtract. So if we add a reactant, you have to subtract the reactant by going to product. So the reactant concentrations will decrease on their way to reestablishing equilibrium, and my product concentration will increase on the way to reestablishing our K value. Okay, let's get back our equilibrium here and see what happens with the next one. The next one, we removed ammonia. Now, there's a variety of ways we can do this. Sometimes they take advantages of different densities of gases and can bleed off different types of substances. If it's an aqueous solution, sometimes we can precipitate and get that out of the way. Okay, but somehow we've removed ammonia. So remember, if you remove, you have to replace. So if I remove ammonia, I have to replace the ammonia. So that means, again, I'm going to go to the product side. Reactants will decrease, my product will increase. Let's see what it looks like with our little, line. So that represents equilibrium. Here comes my stress. Here's my stress. I've lost ammonia. Now, my answer isn't what happened during the stress. My answer is, what do I do to get back? So I want to get this line back even. So I'm going to increase my products and decrease or consume reactants. So I'm going to decrease or consume reactants, and I'm going to form or increase my products. Now, heating the vessel, let's take a look at that. You can think of heat just like what we did with a reactant. So let's get our line back again. Now, since heat, and this is key, you would have to know what side to put the heat on, or you're going to get this wrong. Okay, so there's equilibrium. You notice if I heat the reaction, that means I'm adding heat, or in this case, I'm effectively adding a product. So that is what happens to my little level here. You can think of that as a level. So I added heat. So remember, to add, you remove. To remove heat means to move to form reactant. So I'm going to form reactants. So I'm going to or increase my reactants, and I'm going to consume or decrease my products. So I'm going to decrease products to get to equilibrium. Okay? So I shifted to the reactant side. So you're shifting to the side that's the formation is. Okay? Now, if I increase the volume, if you increase volume, this gets back to gas laws. I'm looking for a place to write here. If I increase volume, as long as there's gases present here, I'm decreasing my pressure. So an increase in volume is a means of decreasing the pressure. Now, when we decrease the pressure, this little line becomes irrelevant. We're not going to use that anymore. So I don't know if I can erase this. I'll just rewrite that heat if I need it in a minute. I'll do it right now, plus heat. So I have 2 moles of gas on the product side. I have 3 plus 1, or 4 moles on the reactant, 2 moles on the product side. If you decrease pressure, that means if there's not much pressure in your life, there are opportunities to get more involved in some other things. So you can go to the side with the decreased pressure. You go to the side with the most moles of gas. Remember to only count your gas molecules here. So I'm going to shift to the reactant side, which means I'm going to increase my concentration or molarity, or honestly partial pressure of my reactant, and I'm going to decrease my molarity of my product. Okay, I'm just going to do a couple of others because I think that you'll get the idea. If I decrease my nitrogen, if I remove, I replace. So to replace my nitrogen, I have to shift to my reactant side. So these are going to be formed. In other words, they will increase. These will be consumed. This is, remember, after the stress, what am I doing to relieve the stress? If you increase the pressure, remember you want to go to the side with the fewest moles of gas, and that's our product side. So that means we're going to consume or decrease our amount of reactant, and we're going to form or increase our amount of product. Okay? Now, what if we cool the vessel? Well, with its concentration and temperatures, we can use our little line again. So let me get this back up to equilibrium. So that's level. That represents equilibrium. Now let's look at our stress. If we cool the vessel, that means we're removing the heat as it's formed in this exothermic reactant. So the system will shift to make product and consume reactant. So when I cool, I'm going to shift to the product side. We'll consume or decrease here, and we will form or increase here. Okay, now there's only one last statement I want to make. I'm going to leave the last example to do in class if anybody needs me to do that. It's simply an example of an endothermic, but I want to talk about this real quickly here. If you want to make a lot of product, make quite a bit of money, what we discovered is if we want to go to the side of the fewest moles, if we increase the pressure, remember that shifted to make more product. And if we cooled the vessel, both of these shifted to make more product. Okay? And so high temperatures, or low temperatures, high pressure. So we want low temperatures and high pressures to make a lot of money in the Haber process. Now, when we talked about molarity, volume, and pressure, remember catalysts don't shift an equilibrium. They don't stress an equilibrium. We shift to get back the same K value. When we're doing temperature, the shift gives us a new K value. You're not going to have to calculate it. That's above your level. When we get to AP, we look at some of those effects. But even in AP, we don't really calculate this. The key is you need to know that equilibrium constants are temperature dependent. And that's why temperature is often reported. It's like they're being politically correct. You don't use the temperature in the problem, but the temperature is reported because the K value is not the same if you change the temperature. So others, you get the same K ratio back. With temperature, you get a new one. Okay, hopefully that's enough to get us going in class. Until then, this is, for the last time this year, signing off.